Hello, dear science enthusiast friends. Today, we will dive deep into the heart of the black hole. If you are ready for this adventure, let's get started. Prologue: The Edge of Understanding. Imagine standing at the precipice of the cosmos itself, peering into a darkness so absolute that it swallows light, time, and space. This is not merely darkness as we know it, the absence of illumination, but something far more profound, a rupture in the very fabric of reality. Welcome to the realm of black holes, where the universe reveals its most extreme and bizarre characteristics. The story of black holes is simultaneously ancient and modern. It begins with humanity's eternal fascination with the night sky and culminates in some of the most revolutionary discoveries of the 21st century. As we embark on this journey, we'll traverse from the death throes of massive stars to the centers of galaxies, from the mathematical predictions of Einstein to the stunning images captured by the Event Horizon Telescope, from the quantum mysteries of Hawking radiation to the ripples in space-time detected by gravitational wave observatories. This is a tale of extremes, where a teaspoon of matter weighs billions of tons, where time itself can grind to a halt, and where the known laws of physics break down completely. It's a story that challenges our most fundamental assumptions about reality and forces us to confront the limits of human knowledge. Part 1. Birth of Monsters. Chapter 1. The Death of Stars. Our story begins not with darkness, but with light, the brilliant, sustaining light of stars that have illuminated the cosmos for billions of years. Every star in the universe is engaged in an eternal battle, the outward pressure of nuclear fusion fighting against the inward pull of gravity. For most of a star's life, this is a stable equilibrium, a cosmic stalemate that can last for millions or billions of years. But all equilibriums must eventually break. When a massive star, one containing at least 8 times the mass of our Sun, exhausts its nuclear fuel, the balance tips catastrophically. The fusion reactions that have held gravity at bay for eons sputter and fail. What follows is one of nature's most violent transformations. The core of the dying star, now bereft of the energy needed to support itself, begins to collapse. This isn't a gentle settling, but a catastrophic implosion occurring at nearly a quarter of the speed of light. Within less than a second, the core, which might have been the size of Earth, is compressed to a sphere just a few kilometers across. The density becomes so extreme that protons and electrons are forced together, creating neutrons and releasing a flood of neutrinos that carry away the star's gravitational binding energy. For some stars, this collapse halts when the neutrons themselves provide enough quantum pressure to resist further compression. These stars become neutron stars, objects so dense that a teaspoon of their matter would weigh as much as Mount Everest. But for the most massive stars, even this exotic form of matter cannot halt the collapse. Chapter 2. When Gravity Wins. Recent research has revealed that the path from a dying star to a black hole is far more complex than once imagined. Scientists studying stellar collapse in 3-dimensional simulations have identified not one, but 4 distinct channels through which black holes can form. In what researchers call Channel 1, some massive stars explode in energetic asymmetrical supernovae, yet still manage to leave behind a black hole. The 2025 discovery documented cases where stars with initial masses of 40 and 19.56 times that of our Sun underwent vigorous explosions but couldn't eject all their material. The remaining core, enriched with heavy elements forged in the star's death throes, collapsed inexorably into a black hole despite the tremendous energies involved in the explosion. Channel 2 involves more modest supernovae explosions that may leave behind what astronomers call lower gap black holes, objects with masses between 3 and 5 solar masses, filling a previously mysterious void in our observations. These explosions might look relatively normal from a distance, making them difficult to distinguish from supernovae that produce neutron stars. But perhaps most intriguing is Channel 3, the silent collapse. In 2024, astronomers studying the binary system VFTS 243 in the Tarantula Nebula found compelling evidence that some massive stars simply implode directly into black holes without any supernova fireworks at all. The system consists of a massive blue star orbiting an invisible companion, a black hole about 10 times the mass of the Sun. The remarkable feature of this system is its near-perfect circular orbit, suggesting that when the black hole formed, it produced almost no kick, no asymmetric explosion to disturb the orbital dance. This discovery aligned perfectly with theoretical predictions. When a star collapses completely, the enormous gravitational binding energy, equivalent to hundreds of supernovae, is carried away primarily by neutrinos, those ghostly particles that barely interact with matter. The collapse is so complete, so total, that the star essentially vanishes from the universe, leaving behind only its gravitational signature. As one researcher from the Max Planck Institute for Astrophysics put it, stars can disappear with a fift, not a boom. The implications are profound. For decades, astronomers have documented cases of stars that simply disappeared from our telescopes, leaving no supernova remnant, no expanding shell of gas, no dramatic light show. These vanishing stars puzzled observers, but the discovery of systems like VFTS 243 suggests a solution. Some of these stars didn't explode. They collapsed so completely that they fell into themselves, crossing their own event horizons and disappearing from our universe in the ultimate magic trick. Chapter 3: The Mass Gap Mystery. For years, astronomers noticed something peculiar in their census of black holes. There appeared to be a mysterious gap in the mass distribution. Stellar mass black holes seemed to cluster around 5 to 20 times the Sun's mass, while supermassive black holes at galactic centers weighed in at millions or billions of solar masses. But what about the middle ground? Where were the intermediate mass black holes? The year 2024 brought revelations that began to fill this gap. Two discoveries made headlines, one in Omega Centauri, a globular cluster that is actually the remnant of a small galaxy consumed by the Milky Way, and another lurking near Sagittarius A star, our galaxy's supermassive black hole. These intermediate mass black holes, weighing between 100 and 1,000 solar masses, represent a crucial missing link in black hole evolution. The discovery of these intermediate objects raises tantalizing questions about black hole growth. Do small black holes grow into supermassive ones through a steady diet of gas and stars? Or do they preferentially grow by merging with other black holes, building mass through cosmic collisions? The answer appears to be both, and the story is even more complex than we imagined. Chapter 4: Second-Generation Monsters. In October 2024, physicists announced a discovery that would have seemed like science fiction just a decade ago: evidence of second-generation black holes born from the merger of two other black holes. The LIGO and Virgo gravitational wave detectors picked up two signals designated GW241020 and GW241101 just weeks apart in late 2024. What made these detections extraordinary was the behavior of the merging black holes. In each case, one black hole was significantly more massive than its partner and spinning at an unusual angle to the orbital plane. These characteristics suggest a complex history. The larger black hole had likely formed from an earlier merger and then found a new partner for a second collision. This discovery confirmed a theoretical prediction known as hierarchical merging. In dense stellar environments like globular clusters or the cores of galaxies, black holes frequently encounter one another. When two black holes merge, the resulting black hole carries significant angular momentum. It spins rapidly. This spinning black hole then wanders through its stellar neighborhood until it encounters another black hole, and the dance begins anew. The implications cascade outward. If black holes can merge multiple times, growing with each collision, this provides a mechanism for building up the intermediate mass black holes that have proved so elusive. It also suggests that the most massive stellar mass black holes we observe might have extraordinarily complex family trees, with some possibly having undergone 3, 4, or even more generations of mergers. But hierarchical merging raised a new puzzle. In November 2023, the LIGO-Virgo-Cagra collaboration detected GW231123, the most massive black hole merger ever observed. After the last black hole evaporates, we enter the dark era, when the universe contains only elementary particles and radiation, all at nearly the same temperature, approaching absolute zero. The universe would be a nearly featureless expanse of photons and perhaps stable particles like electrons and positrons, all moving away from each other as space continues to expand. This final state, sometimes called the heat death of the universe, represents maximum entropy, a state of perfect disorder where no useful work can be extracted from anything and nothing interesting can ever happen again. But even this might not be the end. Some theories suggest that quantum tunneling could allow the universe itself to decay into a lower energy state, a true vacuum, in what's called vacuum decay or false vacuum collapse. If our universe exists in a metastable state, a quantum fluctuation could trigger a bubble of true vacuum that expands at the speed of light, destroying everything in its path and replacing it with a universe with different physical constants. Other theories propose cycles of cosmic rebirth, where quantum fluctuations in the dying universe somehow trigger a new Big Bang. The far future dominated by black holes represents one of the most profound testaments to the second law of thermodynamics. Despite being among the most ordered, structured objects in the universe, black holes ultimately succumb to disorder, evaporating away and contributing to the universe's inexorable march toward maximum entropy. Part X, The Dark Matter Connection. Chapter 30, Primordial Black Holes and Cosmic Mysteries. One of the most intriguing possibilities in modern cosmology is that black holes formed not from dying stars, but in the first fractions of a second after the Big Bang. These primordial black holes, or PBHs, could have formed from quantum fluctuations or density perturbations in the early universe, collapsing directly without needing stellar evolution. The idea was first proposed by Soviet physicists Yakov Zeldovich and Igor Novikov in 1966, with Stephen Hawking conducting the first detailed study in 1971. For decades, primordial black holes remained a theoretical curiosity, but recent developments have thrust them into the spotlight as potential candidates for dark matter, the mysterious substance that makes up approximately 85% of all matter in the universe, but doesn't interact with light. Traditional dark matter candidates, like WIMPs, weakly interacting massive particles, have proven elusive despite decades of experimental searches. No particle accelerator has created them, no underground detector has found them, no satellite has seen their annihilation products. This failure has led physicists to consider alternatives, and primordial black holes have emerged as a compelling option. The appeal is straightforward. Unlike hypothetical particles, we know black holes exist. They require no new physics, no exotic particles, no modifications to the standard model of particle physics. If they formed in the early universe, they could be floating through space right now, invisible but gravitationally influential, providing exactly the dark matter we observe. The mass range for primordial black holes that could constitute dark matter is surprisingly broad. Studies suggest several promising windows. Asteroid mass PBHs ranging from about 10 to the 17 to 10 to the 23 grams, roughly the mass of large asteroids down to small mountains, and stellar mass PBHs from about 1 to 100 solar masses. Each mass range has different formation mechanisms and observational constraints. In 2016, shortly after LIGO's first detection of gravitational waves from merging 30 solar mass black holes, 3 independent research groups proposed that these black holes might be primordial. The idea was revolutionary. Perhaps all dark matter consists of primordial black holes, with some clustered within galactic halos where they could occasionally merge, producing the LIGO signals. The debate was immediate and intense. Some calculations suggested LIGO's merger rates were consistent with primordial black holes making up all dark matter. Others argued the rates proved PBHs could account for less than 1% of dark matter. The discovery by LIGO and Virgo of black holes in unexpected mass ranges has strengthened interest in primordial origins. Some detected black holes fall in what stellar evolution theory calls the pair instability mass gap, a range where normal stellar collapse shouldn't produce black holes. Stars massive enough to form black holes in this range should instead undergo pair instability supernovae, exploding completely with no remnant. Yet LIGO detected mergers involving black holes of 85, 100, and even 140 solar masses. How did they form? One possibility is hierarchical merging, black holes that formed from earlier mergers, building up mass in multiple generations. But another possibility is primordial formation. If these black holes formed in the early universe from density perturbations rather than stellar collapse, the mass gap doesn't apply. The detection of such black holes has breathed new life into primordial black hole theories. Chapter 31. The Fine-Tuning Problem. Creating primordial black holes that could account for dark matter requires exquisite fine-tuning of conditions in the early universe. Bernard Carr, one of the pioneers of PBH research, freely admits this challenge. The abundance of primordial black holes depends critically on the amplitude of density fluctuations in the infant cosmos. If fluctuations are slightly too small, no PBHs form. If slightly too large, too much of the universe collapses into black holes, leaving no ordinary matter to form stars and galaxies. The sweet spot appears to be incredibly narrow. About 1 part in a billion of the universe's energy density should collapse into PBHs at the right epoch. Anne Green, a physicist at the University of Nottingham who has authored comprehensive reviews of primordial black holes as dark matter, notes that no one has convincingly explained why nature would sit precisely at this critical threshold. The primordial density fluctuations are well understood at large scales. They're what seeded galaxy formation. But the small-scale fluctuations needed for PBH formation operate in a different regime. Various inflationary models can produce the right fluctuations, but each requires specific, finely tuned parameters. Despite these challenges, several formation mechanisms have been proposed. One involves cosmic inflation, producing enhanced fluctuations at small scales through features in the inflationary potential. Another mechanism involves cosmic strings, hypothetical one-dimensional defects in spacetime that could collapse to form black holes when they loop. A third possibility involves first-order phase transitions in the early universe, where the vacuum energy changes suddenly, creating conditions for black hole formation. In 2024, researchers explored a novel mechanism involving Fermi balls, collections of dark fermions trapped in false vacuum during a phase transition. These Fermi balls could collapse to form primordial black holes under specific conditions. The intriguing aspect of this scenario is that when these PBHs later evaporate via Hawking radiation, they would emit the same dark matter particles that originally formed them, potentially creating detectable signatures in experiments. The September 2021 announcement by the NanoGrav collaboration added another dimension to the primordial black hole story.
NanoGrav detected a low-frequency gravitational wave signal that could potentially be associated with primordial black holes. If confirmed, this would be the first indirect evidence for PBH formation in the early universe, opening a new window on their properties and abundance. Chapter 32. Constraints and Windows. Not all mass ranges are viable for primordial black holes' dark matter. Decades of astronomical observations have placed stringent constraints on PBH abundance across most of the mass spectrum. These constraints come from multiple sources, each sensitive to different mass ranges. For very small primordial black holes, those with masses less than about 10 to the 15 grams, Hawking radiation becomes important. These tiny black holes would have evaporated by now, potentially leaving behind Planck mass relics. The gamma rays from their evaporation would have been detected, and since we don't see an excess gamma ray background, we can constrain how many such PBHs existed. For intermediate masses, roughly 10 to the 20 to 10 to the 24 grams, about the mass of large asteroids, gravitational lensing provides powerful constraints. If a primordial black hole passes between Earth and a distant star, its gravity would bend the star's light, causing the star to temporarily brighten, a phenomenon called microlensing. Large surveys have monitored millions of stars looking for such events. The non-detection of excess microlensing constrains PBH abundance in certain mass ranges, though a 2019 study opened up the possibility that asteroid mass PBHs could still account for all dark matter. For stellar mass PBHs, 1 to 100 solar masses, constraints come from multiple sources. Dynamical effects in globular clusters and ultra-faint dwarf galaxies limit how many stellar mass black holes can exist without disrupting these systems. X-ray and radio observations of gas accretion onto black
holes in our galaxy constrain the local PBH density. Gravitational wave observations from LIGO Virgo provide information about the merger rate of stellar mass black holes, which must be consistent with the overall population. The cosmic microwave background radiation, the afterglow of the Big Bang, also constrains primordial black holes. PBHs would have affected how matter clumped in the early universe, leaving imprints in the CMB's temperature and polarization patterns. Detailed analysis of CMB data from the Planck satellite places limits on PBH abundance across a wide mass range. Large-scale structure provides another constraint. The distribution of galaxies and galaxy clusters depends on how matter was distributed in the early universe. If primordial black holes contribute significantly to dark matter, they would affect structure formation in ways that must match observations. Despite all these constraints, several mass windows remain open. The most promising are around 10 to the 17 to 10 to the 23 grams, asteroid to mountain mass, and 1 to 100 solar masses. Recent studies suggest that an extended mass function, PBHs with a range of masses rather than all having the same mass, could fit within observational constraints more easily than a monochromatic distribution. Chapter 33. Testing the Primordial Hypothesis. How can we test whether primordial black holes constitute dark matter? Several observational programs are underway or planned. One promising avenue involves searching for micro-lensing events with next-generation surveys. The Large Synoptic Survey Telescope, now called the Vera C. Rubin Observatory, will monitor billions of stars, potentially detecting rare micro-lensing events from asteroid mass PBHs. Gravitational wave astronomy offers another powerful probe. Future detectors like LISA will be sensitive to mergers of intermediate mass black holes, 100 to 10,000 solar masses, filling the gap between LIGO's stellar mass detections and electromagnetic observations of supermassive black holes. If LISA detects a significant population of intermediate mass black holes, especially in merger rates consistent with primordial formation, this would support the PBH dark matter hypothesis. The distribution of supermassive black holes in the early universe, observed by the James Webb Space Telescope, provides indirect evidence about primordial black hole formation. If sufficiently massive primordial black holes existed, they could serve as seeds for supermassive black holes, helping explain how billion solar mass black holes formed less than 1 billion years after the Big Bang. The September 2022 proposal that PBHs explain the unexpectedly large early galaxies discovered by JWST highlights this connection. Searches for Planck mass relics, stable remnants left behind by primordial evaporating black holes, represent another approach. If very small PBHs formed and evaporated, they might leave behind Planck mass, 10 to the -5 grams, remnants carrying all the information that fell into the black hole. These relics would be an exotic form of dark matter, and various experiments could potentially detect their interactions with ordinary matter. Perhaps most intriguingly, primordial black holes could occasionally be captured by neutron stars. Once inside a neutron star, a PBH would slowly consume the neutron star from within, eventually converting it into a black hole. Observations of very old neutron stars, combined with constraints on their survival rate, place limits on the abundance of certain mass ranges of PBHs. Some proposals suggest searching for unusual neutron star properties that might indicate a primordial black hole lurking inside. Chapter 34: Dark Matter Alternatives and Combinations. The primordial black hole hypothesis doesn't necessarily require that PBHs constitute all dark matter. Many scenarios involve PBHs as one component of dark matter, with the remainder consisting of particles. This mixed dark matter approach can satisfy observational constraints more easily than pure PBH models. For example, asteroid mass PBHs might make up 10 to 20% of dark matter, with the rest being axions, hypothetical ultra-light particles predicted by some extensions of the Standard Model. The combination could explain various observations better than either component alone. The PBHs would provide the gravitational seeds for early structure formation, while the particle dark matter would fill in the detailed distribution of matter in galaxies. Another intriguing possibility involves primordial black holes interacting with particle dark matter. If WIMPs or other dark matter particles exist, they could be captured by primordial black holes and accumulate inside them. The PBHs would act as dark matter collectors, creating dense concentrations that might be detectable through their gravitational effects or through annihilation radiation from the captured particles. The idea that dark matter might not be a single substance, but rather a mix of different components, what cosmologists call multi-component dark matter, has gained traction. Just as ordinary matter consists of many particle types, protons, neutrons, electrons, neutrinos, photons, dark matter might also have complexity. Primordial black holes could be one component in this rich dark sector. Recent theoretical work has explored whether primordial black holes could generate particle dark matter through Hawking radiation. The 2024 study on Fermi balls collapsing to PBHs during phase transitions showed that when these PBHs evaporate, they emit boosted, high-velocity dark matter particles. If these particles interact with electrons, they could produce detectable signals in experiments like Xenon 1T, Xenon NT, Super Kamiokande, and the future Hyper Kamiokande. This mechanism connects PBH formation to particle dark matter in a testable way. The gravitational wave background, the combined rumble of all black hole mergers throughout cosmic history, might reveal information about dark matter composition.
If primordial black holes make up a significant fraction of dark matter, their merger rate would contribute distinctively to this background. Future gravitational wave observatories sensitive to a wide range of frequencies could distinguish the PBH contribution from other sources. Part 11. The Information Paradox, Latest Developments. Chapter 35. The Paradox Refined. As we explored in Part 1, the black hole information paradox arises from the apparent conflict between quantum mechanics and general relativity. Quantum mechanics demands that information cannot be destroyed. The complete quantum state of a system at one time should allow you to calculate its state at any other time. But black holes seem to violate this principle when they evaporate via Hawking radiation, apparently destroying the information about everything that fell in. In recent years, the paradox has evolved beyond Hawking's original formulation. Modern discussions focus on several related puzzles, each highlighting different aspects of the information problem. The Page curve, a graph of how the entropy of Hawking radiation should evolve, has become central to judging proposed solutions. Don Page showed in the 1990s that if black hole evaporation is unitary, information-preserving, the entropy of the radiation should first increase as the black hole evaporates, then decrease after about halfway through the evaporation process, the Page time, finally reaching zero when the black hole completely evaporates. The challenge is that Hawking's semi-classical calculation predicts the entropy increases monotonically until the black hole disappears, never decreasing. This contradiction between the Page curve and Hawking's calculation crystallizes the information paradox in a mathematically precise way. 2019 breakthrough. In 2019, physicists made what many considered a breakthrough towards resolving the paradox. Ahmed Al-Mahiri, Netta Engelhardt, and their colleagues, working independently from Jeff Pennington at UC Berkeley, demonstrated how to calculate the Page curve for certain theoretical black holes in a way that was consistent with information conservation. Their approach used tools from quantum information theory combined with the ADS-CFT correspondence, a mathematical relationship between gravity in anti-de Sitter spacetime and quantum field theory on its boundary. This correspondence, proposed in the late 1990s, had already provided strong evidence that information is preserved in black hole evaporation, but the 2019 calculations showed explicitly how information escapes. The key innovation involved computing what physicists call quantum extremal surfaces, surfaces in spacetime that minimize a